First of all, let's look at number sets. Before we look at number sets, let's first of all appreciate what is meant by a set. Now, sets are a form of classification in which entities or things are grouped based on certain characteristics that they have in common. So anything or members of a set would have a particular set of characteristics that is common to them only, and anyone else who does not have those characteristics, who does not meet that criteria, is not a member of such a set. We're familiar with some number sets. Maybe let's say even numbers. That's a set of numbers. They fulfill a particular criterion, where the criterion in question is whether or not that number is divisible by 2. If that number is divisible by 2, we say it falls in within a number set called even numbers. 4 is a member, 12 is a member, 2,580 is a member, but 7 is not a member because 7 does not fulfill the necessary criteria, which is it doesn't have that characteristic of being a multiple of 2. So having said that, we see that there are some other sets, classifications. You can have prime numbers, you can have specific set looking maybe at factors of one particular number, factors of 12 or multiples of 16, that sort of thing. However, we are going to be focusing on the 8 generic number sets. Generic number sets, which are not specific to any particular type of thing. These numbers are called complex numbers. They all belong to a superset called complex numbers. You'll see why some numbers that don't look complex are actually considered to be complex numbers. Let us get in and start defining them. If you look at this Venn diagram here, it's an illustration of the number sets. We'll see the big rectangle, the blue rectangle there, complex numbers. It means all numbers that we are dealing with, or all numbers that we really appreciate as being in existence are called complex numbers. All numbers. We'll see there that complex numbers are defined as A plus BI. We will get into that definition in a short while. Then, of course, inside the complex numbers, let's start off with the imaginary numbers. We will not get into the pure imaginary numbers because what's important is just to know that there are imaginary numbers, regardless of the type of imaginary numbers. So we're just going to limit ourselves to the fact that there are imaginary numbers. Imaginary numbers are defined as 2 plus a certain number that exists, which is the square root of -1. So such a number does not really exist in real life. It is called an imaginary number because of that. Yes. Another imaginary number by definition really would be A plus BI. We'll look at the definition of I, which is just the imaginary figure, where I is the square root of 1. When dealing with roots and square roots, you have a better appreciation as to why we don't have a square root of -1. But basically, a negative number does not have a square root. Then we get into real numbers. These are numbers that actually do exist. And the first number that we'll see there is, first of all, let me say the definition of real numbers is A plus 0i. Remember, we said complex numbers are A plus BI. So if we now give B the value 0, that's when we get real numbers. So that is why we're saying that real numbers are actually part of a set of complex numbers. However, they exist in situations where we assign the value of B in the definition of complex numbers, A plus BI. We assign the value of B 0, which would then mean it's A plus 0i, where we said I is the imaginary figure. So because of that, Remember, if you multiply anything by 0, you're basically eliminating it. So real numbers are a plus 0i, or just a plus 0, or just a. So we've gotten rid of the imaginary figure I. That is how we can now say that real numbers are actually a subset of complex numbers. Inside real numbers, we have two major sets. There's a set called rational numbers and a set called irrational numbers, where we'll see the definitions there. Irrational numbers are numbers that cannot be written in the form of integers or in the form of vulgar fractions, x over y. We also then have a set called rational numbers, where the rational numbers are the numbers that can be written in that format, x over y. Inside the rational number set, we have integers. Integers are a special type of rational numbers where the x over y has y being of the value 1. All integers are numbers who have a denominator of 1 and therefore are just written as whole numbers. In there we also have a subset just called whole numbers, which are integers but excluding the negative values. And then in there again we've got the most nuclear form or the most nuclear set of numbers there called natural numbers, or just counting numbers. These are whole numbers, but we start off with 1. This is how you count. They're called natural numbers because anyone who has not studied any level of mathematics sees these as numbers. You start asking your 3-year-old cousin who's in preschool to count. They start counting from 1. That's the natural way of counting, starting from 1. So that's why we call them natural numbers. So these are the descriptions though. You've seen the illustration in the set as a Venn diagram. Here they are with actual descriptions in case you want to familiarize yourself. Actually, it's not in case. You really need to know the definition. A natural number, these are basically whole numbers from 1 upwards. In short, the short description is that. Whole numbers whose symbol there is a W. Notice now that the symbols would be letters of the alphabet, but they are written in such a way that they are outlines, or at least part of the letter is an outline. So the N is for natural, the W for whole. These are integers starting from 0 going upwards, numbers. The set integer is written as Z. There's a reason why it is Z. I think it was the original name was in German, something before it was adopted as just integer. So the word started with Z. The same thing applies with the the Q for rational numbers. It was also in a different language, maybe Latin or French. But when it was universalized, we retained those letters, but changed the name. Well, we're using English names here. Okay, so integers are all positive numbers and negative numbers, which are whole numbers. In other words, which are written as fractions whose denominator is 1. And then we have rational numbers. Rational numbers are similar to integers, but the difference now is that the denominator can take any value, whether it's 1 or any other value. Let us look at the set notation there. First of all, before we proceed, N, the natural numbers, is a set that equals, and then the open brackets, those curly brackets there, or braces as they're sometimes referred to. You start with 1, comma, 2. The first number that you write there, if you start with 1, it means you're basically saying that the smallest value that's allowed in that set is going to be 1. And then you establish a pattern, 1 followed by 2, followed by 3, and so on and so forth, up until the end. So it doesn't end, so you can just use that dot, 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 and close that brace. The same thing applies with the the whole numbers, we are now saying the smallest allowed value there is the 0. And then we continue counting those numbers. It also does not end. Here with the integers, we see that the smallest allowed value is not a number that we can actually show. It's not a number that actually exists because there is no smallest allowed value. So that's why we start saying it starts from somewhere. That's why I have that dot, 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 dot. And then we end up with -3 and -2, -1. We're seeing a pattern there. The pattern is just keep adding 1. So it basically means that the set of integers, we just keep adding one whole number from an unknown negative number, the smallest possible number that exists, to the largest possible number that exists, which doesn't really exist. So that's why we have that dot, dot, dot there. That is the simple notation. Now, as we get to the rational numbers, we see that the notation now, instead of just listing the sets, we can now use set notation to define the sets rather than listing them. So to define the set there, we are saying there that Q, the set of rational numbers, is equal to any value of X, where you see that vertical bar now between the X's is actually saying Q is equal to X. Then the vertical bar is saying where, defining X, where X is equal to A over B. Q is any value of X. Or the set of Q comprises of all the numbers X, where X fulfills this criterion that it's A over B. And A itself and B themselves are both integers, but B is not 0, is not equal to 0. So in other words, any number that can be written in the format of X over Y or A over B, such that A is a whole number, or an integer rather, and B is an integer as well, any integer apart from 0. That's what we refer to as rational numbers.
Like this video and subscribe to this channel for more such content.